Hello, here we are talking more about exponential growth and decay type stuff. Before we were kind of talking about the functions in general, not really applied to real life. I mean, I think we did a few applications, but it was mostly just kind of learning about the functions and their graphs and behaviors and then logarithms. But now we're going to see kind of specifically, if you worked in a field that dealt with exponential functions, how would you, based on some data that you collected about the subject you're studying, how would you go about finding an exponential function that can model your data? So this is probably, of course, the most useful section in this chapter. But we had to learn all we learned to actually understand how to do this section. So without further ado, anyway, this is section 4.5. Where are we? Section 4.5, Exponential Growth and Decay. And we'll be modeling data. So the first thing I wanted to mention is kind of the basic model for exponential functions. I'm going to kind of write it at the top here. See how we can write this out. So the basic model, it's up to you if you want to write this down. I think it'll be helpful, especially if you've never done these types of application problems. We're going to write it, it kind of looks like it's a function, but we call it A for amount. We'll call that, amount. I'm going to say it even more specifically at time t. Okay, equals, and then it's a with a little subscript of 0, and then e to the kt. This is kind of the model we'll be using in these examples. So let's see, the function a of t is the amount of time. This a with a little subscript of 0 is the initial amount, of whatever it is. So like if it's financial, like you have a savings account, then the a sub 0, the a naught, that would be the initial amount of money that you put into the savings account. Or like if it's population growth, a naught would be the initial population in the first year that you're starting to study this population. And then e, remember e is just a number. It's like 2.7 ... It's a button on your calculator, so don't think that's a variable. That's just a button on your calculator. Let's see, k is a constant, some kind of constant value that's to be determined. I'm just gonna say that'll be the hardest part, is figuring out that k value. But based on whatever information that we're given, we should be able to figure it out. But that'll be the kind of the hardest thing. And then little t will be, of course, time. And then they should tell you sometimes time will be measured in months, sometimes in years, sometimes in days. Usually it's years. But yeah, so that's kind of all the pieces of the puzzle there. That'll kind of keep us on track for these problems. So okay, with that in mind, let's see about these objectives here. The first one says we have, in the year 2000, the population of Africa was 807 million, and then by 2011, so 11 years later, it had grown to 1,052 million. Okay, fair enough. So for the first part, they want us to use the exponential growth model, so kind of the same one that we wrote above, where t is the number of years. Okay, that's good. They kind of told us what t was measured in. It's measured in years, and it's not just years, it's number of years since 2000, to find the exponential growth function that models the data. Okay. So first, we just want to know what that guy looks like, the a. I guess you could write a equals a naught, e to the kt, or you could write a of t. I kind of like a of t because it reminds you this is a function. A is a function of t. A will change depending on what t is. But let's see. So remember, we're kind of remembering what parts are which. So it's like t is going to be your variable. So in this first part, we're not going to necessarily want to fill in what t is. It's not like I need to figure out what t is. T is going to be your variable, kind of like x. If you have a function, there should always be an x somewhere in your equation. And then a of t is the kind of like the function name, like f of x. So t is your variable, like x. And we're used to just seeing an x in the function, so don't worry about him going away and being replaced with a number. You should see the t in your answer in this part. And then a of t, kind of the same thing. It's like f of x. So those ones are fine as they are, but our job is to figure out the values of the other variables, the a sub 0 and k. And I would say the e as well, but remember, e is just a number that we already know. It's that number on your calculator that goes on forever and ever. So this is kind of our objective here, really. Usually the a sub 0 is the easy one, because remember, a sub 0 is the initial amount of whatever, in this case population. Initial amount, or the initial population. But it sounds like, from the language in this problem, they said that t is the number of years after 2000. So I think when they talk about the initial population, they mean the population in the year 2000. Because that sounds like that's when we're starting to study this population. It's the, population in the year 2000. In the year 2000. And they said it in the problem, it's 807. And they put it in million, they put the word million afterwards. But I don't think we have to put 807,000,000 in the problem. I think it's just understood that this is going to be in millions. So at least that's something I can fill in. A of t is, and then it's supposed to be a sub 0. So that, but I can replace that guy with 807 because we said that's the value for this problem anyway. E to the k. Now that's the part I got to figure out. That's kind of the hard part. Usually the initial amount, a sub 0, is something given. You just got to figure out which number given is the right one. K we have to find out. So k we'll find out using some other value of t, so time, and amount that was given. So we'll use a future time. That's kind of the idea, and amount to find k is the idea. Because it's kind of like, we filled in a sub 0 with 807. That was the population in the year 2000. So I think that's not going to help us find k, because that helped us find a sub 0. But they did say in the year, 2011? So when a of t is 2011, they said. Is that the year they said? Yeah. Wait, dang it. The year, is 2011. The amount, or the population, was, what did they say it grew to? It was 1,052 million. Okay, 1,052 million. So I got to figure out what to do with that. Well, if the year is 2011, they said t represents the number of years since the year 2000. Because that's how they described it in the problem. The years since 2000. Well, in 2011, 11 years have passed, obviously, since 2000. So I think that's what we can do, is plug in 11 for t. We're going to plug that into this function. T equals 11. And then we said a of t at that time is 1,052, because that was the population in that year. So if we kind of substitute those guys in, a of t, that guy's going to be 1,052. And then what else? Equals 807. Okay, that's just going to stay the same. E is a number we know, like I said. K is what we don't know. We want to figure that out. Times t, but we said that in this specific instance, in the year 2011, t is going to be 11. So now that we have this equation where a of t is filled in and so is little t, the only thing we don't know is k. Now we're done. We're done if we solve for k. Solve for k. Okay, and then we're all done. So let's see. If I want to solve for k, I think I'm trying to isolate it. So what I would do first is divide by 807. Yeah, 807 on both sides to get rid of him. So it'll be the 1,052 divided by 807. And then I think I can write the right side as e to the 11k, just to make it simpler looking. So I'm dividing both sides by 807, and I think like we said before, you could make the left side a decimal right now, but then you'd be rounding, and then you might round later again and again every time you make some kind of step. But the more times you round, the less accurate your answer is going to be. So I think I'm going to wait to divide those till when I'm done. Okay, now the e to the 11k is all by himself. And like we learned before, if you want to solve an exponential function, an exponential equation, you have to take a log of both sides. But the log that we've seen that balances out an e to a power is natural log, because it has a base e. It has a base that matches the base of the exponential. So I should cancel that e base out here, and it should just leave me with 11k. So the left side, of course, is getting uglier and uglier. It's ln of, let's see, sorry, this is kind of getting ugly. I'm going to move this over here. ln of 1052 over 807 equals, and then we said the e's gone, now it's just 11k. So my answer should be the left side, but divided by 11, because that'll be how I get k all by itself. So k, the exact answer is ln of 1052 over 807. So whatever I get for that natural log divided by 11. And let's see what that comes out to. Okay, it's about 0.024, I'd say, something around there. And that kind of represents the growth rate of the population or whatever it is. All right, so we found k. Now I can fill it into the function. It was a of t equals, what did we say, a sub 0, but we already knew a sub 0 was 807, and then e to the k, which is 0.024 t. So like we said, a of t is like your function name. It's like f of x. So that should just stay as is. And same with t. T is like your variable x. So I guess the beauty of this function is now I should be able to plug in any future year. Like if I want to kind of project, okay, well, what will the population of Africa be in, I don't know, the year 2050? Well, all I have to do is figure out how many years have passed between the year 2000 and the year 2050, which is 50, of course. And I'll just plug 50 in for t. And that should tell me the population in the future. So that's kind of the beauty of all the work we just did, is I can figure out any future population, supposedly, from this function. And of course, it's not going to be exact because things change, you know. Populations aren't growing exactly as they were before. Like, unfortunately, natural disasters happen, which will decrease the population, or, you know, populations increase faster all of a sudden for all kinds of reasons. But it's just kind of a estimation, I guess, just if you want to estimate. For, of course, resource purposes, maybe I want to prepare for the future. I need to know how many resources we need for the people that we'll have in this year or that year. But anyway, there's a part 2 here. We're going to use that function that we found to do something. They want to know, let's see, by which year will Africa's population reach 2,000 million? Which sounds kind of wrong, huh? 2,000 million, what the hell does that mean? But in other words, 2 billion. It's okay. That's kind of confusing, but if I want to rephrase that, I guess what I'm saying is, when will the population, which is more specific, but in general, we've been calling that the amount, because in these exponential functions, we don't really know if we're talking about population or like the amount of bacteria or the amount of radioactive substances. So in general, we're talking about amount here. When will the population or the amount reach 2,000? But in our function, we said a of t represents amount. That's what we're going to have to do, is just substitute a of t with 2,000 and then solve for t. Which makes sense, because if we solve for t, that should tell us time, and that's what they want to know, by which year. So I guess that kind of makes sense. So I'm going to bring my function down that we found from part 1. Let's see, from part 1 above, it was a of t equals, we said a sub 0 was 807, e to the k, I believe, was 0.024 t. Let me make sure I got that right. Okay, that could mess it up if I got k wrong. But like we said, we want to know when will the a of t, the amount or the population, reach 2,000. So that's what we're going to do, is replace it. But everything else is staying the same, because we're still talking about the same, the population of the same place and the same years and all that stuff. Now we have to solve for t, but we almost kind of did this in the first part. We solved for t. It was just there was a different number here. It wasn't 2,000. It was, what was it, 1,057 or something like that. So we want to solve for t at this point. But it's kind of the same step, so I just have to divide by 807, which we've done before. It's just I was dividing 807 into something else, that's all. So it'd be whatever 2,000 divided by 807 is, I don't know, I'll find out later, equals e to the 0.024t. All right. Looks good. And like we've seen before, now if I want to solve for t, the next step is to take the natural log of both sides. So I've got natural log of the left, which is natural log of 2,000 over 807, okay, and the natural log of the right. And the beauty of that, like we said before, is natural log and e cancel each other out, because the natural log is a log base e. And if the base of the log matches the base of the exponential, they should cancel. So left side, same thing, 807. Okay, the right side, though, all we're left with is the exponent, 0.024t. And I think we can solve this if we just divide both sides by 0.024. So I'm just going to rewrite this again because I kind of ran out of room down there. ln of 2000 over 807, okay, equals, it was 0.024t. But we said we can solve this all the way by dividing by 0.024. And that should do it. Let's see. Okay. So t should be that terrible number on the left side. ln of 2000 over 807, all divided by 0.024. But I think I'd like to know kind of approximately what that is equal to. ln of 2000 divided by 807, okay, whatever that is, divided by 0.024. Let's see, so I'm getting about 37.8 or so, something like that, years. But you know, they said, what year will that be? And what if someone asked you, okay, what year will this happen? And you said 37.8. They say, what the hell? You mean like 37.8 AD, like in the past? No, but what you really mean is 37.8 years after the year 2000. Remember, that's what this whole problem was saying. So it's 37.8 years after the year 2000. So it'll pretty much happen in 2038, I guess, you know, if you round up. It actually happened at the end of the year 2037, but whatever. I guess we're rounding here. That's not that far away, huh? Yeah, that's the interesting thing about exponential functions. You just, the outcomes like that you don't expect. You think, oh wow, 2,000 million, that's a lot of people. That's not going to happen for a long time. And then all of a sudden, it's a year that's not that far away, and you say, oh crap. That's how populations work. But, you know, a lot of times there's something, I don't know, something that'll change. You never know. But let's see, now what's the next problem talking about? Now we want to, oh, this is part 2. Let me see, what was part 1 of this guy over here? Population of Israel, okay, in 2000. So we're kind of talking about the same initial year, 2000. The population of Israel was approximately 6.04 million. Okay, let's see. Okay, interesting. And then by 2050, it is projected to grow to 10 million. Okay, that's interesting. It's like someone must know the exponential function already, or else they wouldn't know that projected, you know, population value, right? But so they want us to find, use the exponential growth model, same kind of thing where t is the number of years after 2000, to find an exponential growth function that models the data. Okay, so kind of the same directions as the last one. So I think if you kind of understood the last one, then this one will go a really similar way. It's like, this is our model. Okay, it looks like this. The first thing that should be easy is a sub 0 is the initial population. I should be able to just fill in the number there. Let's see, a0 is the initial population. But in this problem, just like the last one, when we talk about initial population, we mean the population in that furthest year back that they've been talking about, 2000. 2000, okay, and they said that was 6.04 million. And I think just like in the last one, we can just leave the million part out of it. You just know that these answers are going to be in millions. No need to really, like, you don't have to write all the zeros. So I'll just put 6.04 here, and then e to the kt. So our job was to fill in the a sub 0, but now the more difficult job is to find out what k is. Find k using, you know, like we kind of described before, some kind of future value. So we're going to use where t is, let's see, the next year that they mentioned is 2050. But t represents the number of years since 2000, so t would be 50 there, because 50 years have passed since the year 2000. And the population at that time, or the amount at that time, is going to be 10 million. So I should be able to replace t with 50, and then a of t with 10 million. And then the only variable I won't know is k, and I should be able to solve for k. Then solve for k is kind of the idea. And I know these problems, if you've never seen them before, it's like, man, there's a lot of steps here. But you can kind of get the hang of them after you do a bunch of them, which is good. But it doesn't mean it's easy. This stuff is not easy. Yeah, so let's try to substitute those guys in here. We got a of t, we said, is 10 million, because that's kind of the future population projected. And then little t, we said, is going to be 50, because in the second year that they mentioned, 2050, 50 years have passed since the initial year, 2000. E is going to stay the same though, and then k we don't know, so we have to leave it. But really in this equation, now that we've replaced a of t and t, the only thing I don't know is k, because like we said, e is just some number. So at this point, I should be able to solve for k. And it's going to go a really similar way to the ones we've done before. I'm going to divide by this coefficient, or divide by a sub 0. So 10 divided by 6.04 should be on your left side. 10 divided by, let's see, 6.04. Okay, and then on the right side, e to the, I could write that as 50k, I guess, to make it look prettier. K times 50, 50 times k, you know, same crap. And then, now we kind of want to get rid of the e, but like we've seen before, if I take a natural log of both sides, that should knock out that e. There we go. 10 over 6.04 e to the 50k. Alright, yeah, that ln should knock out the e. So now we should just be left with the 50k on the right side. Ln of 10 over 6.04 on the left side. 50k. So then the only thing left to do would be divide by 50. And then we should have k. Once we know k, then we can replace it in the kind of the basic model of the exponential function, and we should be done. So k is exactly ln of 10 over 6.04, that divided by 50. But I kind of want, an approximation, because that's a very ugly answer. And I think, if this had no context, like I was just trying to find a function with no background information, I didn't know what we were talking about, the population or whatever, then a lot of times you do want the exact answer, so I might leave it as it is now. But because this is talking about real life stuff, populations of stuff, I kind of want to know approximations. So anyway, this, I'm coming out with 0.010. Actually, it's like 0.01008 something something something, but it kind of just comes out to 0.010, which you could just start writing as 0.01 if you want, just to make your life easier. There we go. Okay, so our function should be, let's see, a of t is, we said a sub 0 was the 6.04 value, e to the k, but we now found out that k is, approximately 0.01 t. There he is. So that's our beautiful function in all its glory. And like we said before, the beauty of that is now we can kind of approximate any future population of Israel, or some population that's in between 2000 and 2050 if we wanted to. Or we could find out, like we did in the previous one, when will the population reach this certain level approximately? Is that what they're asking in the second part? Yeah, so it looks like, okay, in which year will Israel's population be 9 million? And I'm assuming it's going to be somewhere between the year 2000 and the year 2050, because they said in the year 2050 the population reaches 10 million, and this is less than that. So I'm kind of, I guess just to check my answer in the end, my answer better be between the year 2000 and the year 2050, Between the year 2000 and the year 2050. Like I said, because this guy, in the year 2000, the population was 6.04. In 2050, it was 10. And this number that they're asking about is in between those two. But I should be able to do like we did in the previous example here, is take the function that I found from part 1, from 1 above. Okay, a of t was 6.04 e to the 0.01 t, and then replace the amount with 9, because 9 is the population in the future, or some future amount. So we're going to replace a of t with 9 and solve for the only remaining variable t. And that should tell us what year that'll happen in. And like I said, this is just an approximation, because things change. All kinds of stuff affects population. Okay, so there's 9. 6.04 e to the 0.01 t. Okay. So now we're going to solve for t, and by doing that, we'll just do the same exact steps we've been doing over and over. We're going to divide by that, whatever a of t was, 6.04 in this case. You're going to do this process solving for t so many times, you're going to think you're losing your mind. Ugh, so, okay, 9 divided by 6.04, whatever that is, equals, and now just e to the 0.01 t is left. Beautiful. And now to get rid of the e, like we've seen, it feels like a million times, but this is actually only the 4th time in this video. We're going to take a ln of both sides to knock out that e. Okay. 9 divided by, gotcha. E to the 0.01 t. Alright, fair enough. So the ln and the e should cancel. The left still looks the same so far. Right now, though, you're only left with 0.01t. And I think now we know how to solve this. We're going to just divide both sides by 0.01. Let's see. 0.01, 0.01. That should leave me just t on the right side. So t should be equal to what I see on the left side there, that terrible number. ln of 9 divided by 6.04. All that divided by 0.01. And what is that? Let's see. Okay, I'm getting about 39.9 years, okay, because that's what t was measured in. And it's not only years, but it's years after the year 2000. So pretty much it's going to happen in 2040. Because that, you know, this year is about 40 if you round it up. Alright, so that's not too far away actually, huh? 2040. Oh man, that was fun. Let's see what else we got. This, I mean, if it starts out that fun, I can only imagine it gets more fun than that from here, right? Good times. Alright, the next one is talking about logistic growth models. So this, it has an exponential function in it, but these models, the logistic growth models, they're kind of more realistic in real life. They kind of show how populations would usually grow, because populations don't really grow without bounds usually. Well, it seems like the world's population, humans, is, but like, I mean, animals, I guess. You think about the population of, I don't know, wolves or something in a certain forest. They're not just going to grow forever and ever. They're going to run out of food to eat if there's too many of them to fight over the food. They're going to fight each other. There's going to be humans killing them. There's all kinds of things that'll slow the population growth. So these logistic models are probably more accurate as far as like animal populations, stuff like that. So let's see, what do we got? Just they got one here in this first part. In a learning theory project, psychologists discover that this function, f of t equals 0.8 divided by 1 plus e to the negative 0.2t, is a model for describing the proportion of correct responses after t learning trials. Okay, I gotta remember that. So t is the number of learning trials. So if they tell me the number of learning trials, I'm going to plug it in for t. And then what was f of t? They said the proportion of correct responses. Okay. Proportion of correct responses. All right, fair enough. So the first part, though, what do they want? They want to find the proportion of correct responses after 10 learning trials. So it looks like 10 is something I'm either going to plug in for t or for f of t. So that's kind of my question. Is f of t equal to 10 or t equal to 10? Well, that's why I kind of wanted to make a note here of which one was which. What was the number of correct responses? Oh, sorry. 10 is the number of learning trials. Hello. We're looking for the number of correct responses, huh? 10 learning trials. We said t is the number of learning trials, so it's not f of t that we're plugging in 10 for, it's t. So okay, you're gonna find f of 10 because t is 10. But all the other numbers from the function that they gave me are staying the same. The 0.8 over 1 plus e to the negative 0.02. But now it's times 10 because specifically t is 10. Now I'll put that in my calculator. I gotta do it really carefully though. If you want to be really careful, just because there's a lot going on here, you can always kind of calculate the denominator first. So do 0.08 divided by, okay, now I'm going to figure out what's e to the power of, let's see, e to the negative 0.02 times 10. That guy plus 1, okay. On the denominator, I'm just getting 1.818730,753, something like that. And now I'll divide them. So only because I'm afraid if I type this whole thing in my calculator, I don't know, I might not put enough parentheses or the calculator, I don't know, I might type something in wrong, so I'm kind of worried about the calculator messing up the order of operations here. 3, 0, 7, 9, 3. Okay, I got 0.044 about, I guess if you round it. Yeah, so I think in the context of this problem, this is the proportion of correct responses, they said. Proportion, oh no, yeah. I think that means this is like the decimal form of a percent. Decimal form of percent. So if we want to make it a percent, I would move the decimal to the right twice. So it'd be like 4.4%. So it looks like after 10 learning trials, 4.4% is the proportion of correct responses. That's not that great. Wow. Okay. It's kind of hard to, see if that seems about right, because I don't know what the hell they're talking about here. But I think, let's see, I think now they're asking us a question about the same function in 2b here. What is the limiting size of f of t, the proportion of correct responses, as continued learning trials take place? Okay, let's see. Well, this one, they're kind of helping us out because we don't really know what limiting size means. I guess I think just from the words, the way it's described, I think I would imagine that's the highest that this f of t can become. Kind of like we're talking about with population. If we're talking about the population of an animal, there's going to be a limiting size, or like the highest value that this could become. There can't be more than a certain number of wolves in a certain forest because there won't be enough resources and stuff for them. So it's like, yeah, the highest value is kind of what they're asking for. F of t can become, I guess. And this one, I think like I said, they're kind of giving us the answer because we don't necessarily know what that means. But this way, we'll kind of know what to look for in the next example. The number in the numerator of the logistic growth function, it was 0.8 in this case, is the limiting size of the proportion of correct responses. Okay, so when you see a logistic model, it's kind of the takeaway here. Let me see, takeaway. The limiting size of a logistic model is basically the number in the numerator. It's kind of the highest value that the function can take on. So now we know that. Okay, I think the next problem will be a lot easier. It's okay, in the next problem, what are they saying? There's a new logistic growth function here, f of t equals 100,000 over 1 plus 5,000 e to the negative t. So without even reading the context, I already know that the numerator, 100,000, is going to be the limiting factor. What do they call it? Factor? Limiting size, sorry. I don't even know what they're talking about, but I know now that the numerator's number is always the limiting size. So if they ask that later, I'll know. Size, okay, but what are they talking about? That describes the number of people, f of t, who have become ill with influenza T weeks after its initial outbreak in a particular community. Okay. So it sounds like the largest number of people that could possibly get infected is 100,000. Or become ill, I guess. But first before they ask that is, how many people were ill by the end of the 4th week? Okay. Well, they said T is the number of weeks. Let's see. T weeks after its initial outbreak. So I think in this case, when they say the 4th week, they mean t equals 4, because that's how many weeks have passed. Well, really, I just have to plug in 4 for this function, f of t, but I want f of 4. Well, it was 100,000 over 1 plus 5,000 e to the negative t, but I want negative 4 instead of negative t. And then this I should just be able to plug in my calculator. Let me see. I got, approximately equal to. And I think I'll do the same thing because I'm really paranoid I'll mess this up. I'm just going to work on the denominator. What's 5,000 times e to the power of negative 4? Okay, so I've calculated this. This is on my calculator right now, but I'm going to add 1 to that. So the denominator I'm getting is 92.5781944. And I'm trying to keep as many digits of accuracy as I can. I'm writing down all the digits I see on my calculator screen, because I know I'm going to round again in the end. So I don't want to get too... I don't want to round too many times because it's losing accuracy every time I do. Okay, and if I divide those guys, I'm getting about 1080.17 or so. And I already forgot what this stood for. Well, that's the number of people infected. So I guess this decimal doesn't really make sense in this problem. How can I have 0.17 of a person? So I guess I'll just round it to the nearest whole number. 1,080 people infected after 4 weeks. Okay. But then they want to know what you've kind of already talked about, the limiting size of this guy. We said the numerator of the logistic model is going to be the limiting factor. 100,000 is I don't know how to say it. I'm not very good with language, I guess. Is the largest number of people to be infected by this influenza virus. Is it a virus? Yeah, right? Whatever. Alright, good times. That was fun. This section can only get more fun, right? Come on. We're having a good time here. Okay. Oh, and I think what'll help for the next part is, let me talk a little bit about logistic growth, the graphs. So let's see, like, it's kind of as opposed to an exponential function. We want to kind of compare and contrast exponential graphs versus logistic graphs. So, I mean, a population or an amount of something will grow exponentially if there's kind of nothing to hold it back, which, you know, I've heard people say that's what it seems like the world's human population is doing. There's nothing really holding us back. We don't really have any natural predators or anything, and we haven't run out of resources yet, but we might someday. Not to bum you out, I'm just saying, but the logistic model is more for populations of animals because humans are killing animals off, I guess, and then they don't have enough resources. I guess they're not smart enough to make, I don't know, produce food in factories like we do and all that kind of stuff. So, okay, exponential models, they look like the graphs we've seen before. They kind of go wee like that. But logistic graphs, they look sort of similar at first. They kind of go like this. They're growing, and then all of a sudden there's a certain point where they'll kind of stop growing as quickly and they'll level out, sort of. And actually that level where they're kind of approaching right there, there's going to be, that's the limiting size right there. So that's the highest that it can go. Limiting size. Whatever that y value is there. I'll call it L. So let's call this y value L. Okay, just so we can kind of recognize the graphs, because I think that's important in this next part. Let's see, what do they say here? They want, the table shows the population of various cities and the average walking speed of a person living in the city. Okay. Create a scatter plot for the data. So this one, they've already kind of done it for us. Scatter plot is pretty much just plot the points. So this point, 5.5, comma, 0.06, they've plotted that, I guess about here. That's just barely to the right of 0. And then the next point, 14, comma 1, that's this next guy here that we've highlighted in red. And then 71, comma 1.6, that's about this guy right here. 138, and then 1.9, it should be about here. So you can kind of tell these values are leveling out, you know, at first they were growing really quickly, they were going wee, and then now they're kind of, ooh, I'm slowing down, and I'm kind of approaching some kind of value here. Which in this problem, I think it makes sense, because it's talking about how fast people can walk. It doesn't really matter, like imagine you're walking around New York, there's a lot of people around, so you can't really walk too fast, you know, so I'd imagine that you're not walking very fast there. But if you're kind of on an empty street, maybe in the middle of the night, or it's just a city that doesn't have a high population, you can walk as fast as you want, but it's only a certain speed that a human can walk. You can't walk, you know, as fast as you want forever and ever. Yeah, so I think that's kind of the leveling, what they call it, the limiting factor here. You're probably approaching the limit of human speed as far as walking goes. That's why this guy would probably be more of a logistic function or a logarithmic. Yeah. Logarithmic. Remember we talked about logarithmic graphs. Let's see. What did the logarithmic graphs look like? Just to review a little bit. Logarithmic graph, because we graphed the exponential guy above, just to review. And then logistics, kind of a brand new idea. We kind of graphed that. But I remember a logarithmic graph, it goes like this. Something like that. So if it looks like that versus these guys, maybe I should draw it up here with his friends, huh? You got the exponential graph, you got the logistic graph. Let me add another guy, just so they're all together. Logarithmic graph. Alright, if he goes, it's kind of like, I guess you could tell it's logarithmic. One way is it occurs on only one side of the y-axis. It doesn't cross the y-axis, that's for sure. Yeah, so it looks, okay, so we kind of have an idea. But I think, like they said, a logarithmic function would be a good choice for modeling the data. And it's only because once I plotted those points and I connected the dots, it kind of looked more like, I just look at these three graphs and I say, all right, which one of these guys does it look like? You know, the best, and you just kind of use your best judgment. Now the second problem, we're kind of left to our own devices here. We've got to plot these points on our own. It says, the table shows the percentage of miscarriages by women of various ages. Create a scatter plot for the data. Determine the type of function. You know what? I'm realizing a lot of these applications are kind of bummers, huh? This is bumming me out. Anyway. So a woman's age, okay, if she's 22, her chance of miscarriage is 9%. And then all the way from the age of 22 all the way to 47. And the percentages kind of go from 9, that's the lowest one, to 52. Okay, so that might help us scale the x and y axes because they haven't scaled it for us. So the x values and the y values. Well, it looks like the x values go from 22 to 47, so I guess I could just go... If I start at 0, let's say, what's the furthest to the right that I need? Well, the highest x value is 47. Let's see, x value. It's 47, so, I mean, I guess I could end at 47, but I think a nicer, rounder number is probably 50. And then halfway would be 25, you know, and then... So it looks like 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. That's kind of a good scale, I guess. That'll kind of capture all our values for ages anyway. And then percent chance of miscarriages. Okay, it looks like it goes from 9 to 52. It's kind of a tough one. I guess... Okay, well, it starts at 0. You always want your origin to be in there. But the highest it goes is 52. But it's kind of like 52 is not a nice round number. I might round it up to the next nice number, like 60. Or if you went up to 55, that's fine. This is just kind of... You know, this part doesn't really matter, I guess. You're not going to get marked wrong if you put a different number there. If you put 55, that's fine. But if that's 60, then halfway would be 30. You know, that kind of... Okay. I think from there we can kind of scale what we're doing. Let me try to plot these points. The very first point was 22, 9. So, okay, 22 on the x-axis, 9 on the y-axis. Let's see, 22 is probably about here. And then 9 is about here, maybe. And these don't have to be perfect, okay? You just want to get them as best you can so that you can tell which of those 3 graphs it's going to look like. And then we got 27, 10, okay. Well, that's not going to be much higher. 27, though, is a little bit further out to the right, but then 10 is barely above 9, so it's not really changing much at that point, okay. I mean, vertically anyway. So now the next point is 32, 13, so a little bit of a jump for the y value. 32 is about here. And then 13, if that was 9, I'd say 13 is probably like here, maybe? Somewhere around there. Let's see, and if, like I said, these points, if they're not perfect, I think you're still going to be able to tell what graph it looks like. The next point is 37, 20. Let's see, 37 is past 35, so he's probably right here. 20 is about here, maybe, I don't know. Something like that. And then the next point, 42, 38, okay. 42 is about here. 38, okay, now we're finally higher than 30. These are probably about here, maybe? So a big jump right there. And then the last point, 47, 52. So 47 on the x-axis is probably about here. And then 52 is pretty high up. It's like, maybe about here. So let me connect these dots. It looks like... So now if I kind of look at that graph, it doesn't look exactly like any of the 3 graphs we had above. But I think it most looks like logistic, if I had to say. Because logistic kind of has this, I don't know, to me it looks like an S. I don't know what that looks like to you, but it looks kind of like an S shape. So I think I'd say this guy is a logistic model. Yeah. Man, I don't know why they had to make that about a really bummer subject. Thanks a lot, guys. Okay. Last objective in this section. They want us to be able to express an exponential model in base E. Okay. So you notice the first examples we did about population growth and stuff like that, the functions that we were using were base E. So other times you can use different bases. Like here we have, this looks like the base is 7.8. It's 4 times, but the thing being raised to the power, the base is 7.8. They want us to rewrite that in terms of base E. Just because it kind of makes things nicer. You know, if I wanted to solve this, let's say I want to solve this for x. I'd have to first divide by 4, and then I'd have to take a log both sides, and that log would have to have the same base as this exponential. Log base 7.8, that's terrible. I don't even want to think about that. So I think a natural log or base E is a lot nicer. That's kind of the idea. If you have an exponential function that doesn't have a base E, your life's probably going to be a lot easier if it does have a base E. So this would be the way to go about it. You take the function that was given, okay, whatever it was. You're just going to rewrite it. You're just going to insert kind of, let's see, insert E to the ln power, and then fill in the base here and the x. I mean, because if you think about it, let me see, I'm gonna rewrite what they have here just to kind of illustrate why that's okay. Why can you do that? If you have 4e to the power of ln 7.8x. I mean, if you wanted to simplify that, what would happen? Let's see. Well, remember e to the ln, those cancel, those are opposites. So if those cancel, you're left with 4 and then 7.8 to the x power, which is exactly what we started with. So they're just kind of inserting something that would cancel anyway, you know, so it wouldn't really change the function. But they're inserting it so that nice things happen, pretty much. All right, but instead of canceling, they want to keep the e. So what they do instead is just, they take that ln of 7.8 and they calculate or estimate it with their calculator. So they type in, okay, what's log of 7.8? Natural log, blah, 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 and then they rounded it. Looks like it was 2.054x. So now all of a sudden, this is an equivalent function. So the function that we were given to begin with, the one in the red box, and then the one we just found in the blue box are equivalent. They mean the same thing. So, you know, if you plug in one x value to one and the same x value in the other, you're going to get the same answer. It's just that this guy's a lot easier to deal with. Those try to do that on our own. It's kind of weird. And this is probably something you would never need to do in real life unless you were studying populations, I guess, which, I don't know, not a lot of people do. Only some. It's okay, let's express the answer, in terms of natural log. Okay. And then, so we got, I'm just gonna rewrite the function so I'm all ready for this. 6x, okay. And now we're gonna, like we said, we're gonna insert our own little e to the power. So e to the, but the only way to do that is throw an ln in there as well. Because if I throw an e in there, I better throw in the opposite of that. They better cancel. And then 4.6x. And all I have to do, like we said, is calculate what is ln of 4.6. You know, so in my calculator, I'm going to type this in. What's ln of 4.6? And then kind of approximate it. 4.6. It's about 1.526 or so, something like that. So now I'll just replace that ln of 4.2 with that guy. Y equals e to the 1.526 and then x. So this function should be equivalent to the one that they gave me. Well, that's something like that wouldn't be on an exam. This is not on an exam because it's just hard to remember. It's just good to know that there's a way to do this. For if this is your career someday, that you have to change. You know, you're dealing with exponential functions. An exam. Okay, so don't worry about that. You know, it could be on homework or quizzes, but on homework and quizzes, you can always look back at these notes if you want, and just kind of copy your work and stuff. So just know there is a way, but don't worry about necessarily memorizing all the steps to this last objective, objective 4. Alright, that was fun. Let's do it again in the next video, okay? But we'll have fun in a different way. Different types of stuff. Thanks for listening. I'll talk to you later.